High above Midtown Manhattan, an ironworker steps onto a narrow steel beam, frozen by a single sudden gust of wind. 800 feet below him, thousands of oblivious pedestrians walk past a construction site smaller than an average city basketball court. Directly above those packed sidewalks rises a soaring glass needle, stretching so high into the sky that its upper floors disappear into gray winter clouds. It is 84 times taller than a standard two-story home, yet its foundation is narrower than the length of a single bowling lane. By every established law of traditional building design, a structure built with these extreme physical proportions should simply snap under intense atmospheric pressure. If you built a wooden ruler with these exact ratios, a light breeze would instantly snap it right across your knee. Yet this paper-thin tower stands completely upright, enduring powerful ocean gales that strike the island of Manhattan every single winter. Architects around the world watched the preliminary drawings with deep suspicion, calling the radical proposal an impossible engineering gamble. A single structural miscalculation would not just crack the glass cladding, but could unleash thousands of tons of concrete onto Central Park.
The Steinway Tower isn't just tall, it's the epitome of the pencil-thin skyscraper, a bold statement in glass and bronze.
To understand this modern miracle, we have to look past the shiny glass exterior and venture down into solid Manhattan bedrock. Because long before workers poured a single drop of concrete into the sky, they faced an insurmountable spatial crisis on the ground. New York City real estate is among the most expensive land anywhere on Earth, pushing developers toward radical architectural survival strategies. With zero open horizontal space left to build upon, ambitious builders had only one remaining direction to go: straight up. This specific plot of land was just 60 feet wide, roughly equivalent to the space needed to park 3 yellow taxis bumper to bumper. Standard high-rise designs require massive, broad bases, like a heavy pyramid, to spread structural weight evenly across the earth below. Without a broad base, a tall structure lacks leverage, making it vulnerable to the immense tipping forces generated by ocean winds. As gale-force winds hit the flat side of a tall skyscraper, the building acts like a giant lever, pushing against its own foundation. The higher the building reaches into the sky, the greater that overturning leverage becomes at ground level. At 1,400 feet tall, wind pushing against the upper glass panels generates thousands of tons of lateral rotational force. The tower isn't just trying to slide sideways. The wind is actively trying to rip the entire structure straight out of the ground. Even worse, wind blowing around sharp edges creates powerful mini whirlpools of air that violently tug at the building from side to side. This rhythmic side-to-side pulling can cause entire upper floors to sway so aggressively that light fixtures swing and water sloshes out of sinks. Engineers knew that if they built a conventional square tower on this microscopic plot, the building would quickly sway itself to pieces. Traditional skyscrapers solve strong wind forces by adding internal steel diagonal braces, creating massive cross patterns throughout the outer walls. But on a footprint only 60 feet wide, thick structural steel braces would completely block all windows, rendering interior living rooms pitch black. Another classic fix relies on digging enormous, wide subterranean basements to anchor the tower's heavy lower base deep underground. However, Manhattan sits on an extremely tight grid, packed tight with active subway lines, giant water mains, and century-old basement walls. Excavating horizontally past the narrow property line was legally impossible, locking structural engineers into their tiny 60-foot footprint.
This structural load is unacceptable. It fails the stress test right here.
We accounted for that in the revised model. Check the new figures. It doesn't matter if we can't finalize the seismic review.
If structural engineers made the concrete walls extra thick to stop swaying, the building would become far too heavy for its narrow base. Too much dead weight on a tiny footprint causes intense ground pressure, threatening to crack the subterranean rock formations underneath.
Conversely, making the structural components lightweight would turn the sky-high luxury apartments into a wild, swaying amusement park ride during storms. Computer simulations repeatedly produced catastrophic structural results, showing critical structural stress points snapping under standard 100-year hurricane models. The project was on the absolute brink of total cancellation before work even began at the active urban construction site. A completely new approach to structural physics was desperately needed to turn this theoretical blueprint into physical reality. The architectural team realized they could not fight against the force of high-altitude winds using sheer bulk strength alone. Instead of trying to block the wind like a solid brick wall, the building needed to trick the wind into passing harmlessly by. Designers sculpted a unique, stepping, feather-thin profile that gently tapers back as the skyscraper climbs higher into the Manhattan sky. This subtle architectural stepping breaks up approaching air currents, preventing dangerous wind whirlpools from locking into a destructive rhythmic push. To give the slender tower structural strength without sacrificing windows, engineers concentrated its strength into two exceptionally thick side walls.
Notice how the rigidity it covers provides stability while still remain completely open. A perfect structural analogy.
These thick structural sidewalls act as a rigid spine, absorbing heavy wind loads while allowing panoramic glass windows front and back. Rather than relying on basic steel beams, engineers turned to an advanced material formula never before used in North American residential construction. They formulated an ultra-dense concrete mix capable of carrying intense crushing pressure equal to thousands of fully loaded semi-trucks. Finally, high up in the crown of the tower, engineers reserved space for a secret, high-tech mechanical counterweight system. It was an astonishing engineering blueprint, but moving from a digital computer simulation to real-world Manhattan concrete was pure chaos. The physical build would push high-altitude construction equipment and human crane operators far beyond their normal operating limits. Construction crews begin by drilling deep into the ancient Manhattan schist bedrock, using massive industrial drill rigs operating in tight quarters. Worker crews drive over 200 high-strength steel rock anchors up to 100 feet straight down into solid subterranean granite. These heavy steel anchors work like massive lag bolts, clamping the narrow building down so wind cannot lift the upwind side up. At street level, mixer trucks queue down the block, continuously feeding a high-pressure hydraulic concrete pump running non-stop overnight. Powerful hydraulic pumps push ultra-dense wet concrete straight up through heavy steel pipes reaching over 1,000 feet in the air. If the wet concrete sits inside the long pipe for even 20 minutes, it hardens solid and destroys the entire pumping system. Right now, high-altitude ironworkers assemble solid rebar cages, working in sub-zero winds that whip around the exposed structural core. Every single piece of steel beam must arrive at the crowded site on a precise minute-by-minute delivery schedule due to limited staging space. There is zero ground storage room. Incoming delivery flatbeds drop off materials directly onto crane lines dangling from the upper tower. A custom high-capacity tower crane climbs higher along the exterior face, lifting heavy concrete buckets up into the swirling sky clouds. At 1,000 feet above the street, high winds regularly force crane operators to pause operations to prevent swinging loads from colliding. Suddenly, an unexpected Arctic freeze strikes Manhattan, threatening to freeze the freshly poured high-strength concrete mixture before it sets properly. Workers instantly wrap entire upper floors in thick thermal blankets, using industrial heaters to maintain precise curing temperatures through the night. As the building grows taller and thinner, structural surveying teams continuously check the tower's centerline using high-precision laser targeting equipment. Even a tiny fraction of an inch alignment error at street level would compound into a dangerous multi-foot lean near the top roof line. We are checking laser calibration coordinates 3 times a day, ensuring this tower rises completely straight into the sky. Floor by floor, the ultra-thin structural spine pushes higher, reaching its final structural height of 1,428 feet. To keep this impossibly thin tower stable during ferocious high-altitude winds, 3 distinct structural systems work in absolute harmony around the clock. First, the heavy side walls, cast from ultra-dense concrete, form a rigid structural spine that resists intense bending forces from the side.
This concrete mix has a structural strength rating of 14,000 pounds per square inch, roughly 3 times stronger than standard highway concrete. Second, the building's exterior features decorative terracotta tiles and bronze fins that gently disrupt smooth air currents flowing around the facade. By breaking violent wind into tiny, harmless swirls, these textured exterior panels eliminate the violent side-to-side suction forces altogether. It is passive mechanical engineering built right into the decorative facade. The building actually uses art to survive strong wind. Third, concealed inside the very top stories sits the building's ultimate safety mechanism, an 800-ton tuned mass damper system. This giant device consists of a massive suspended steel weight suspended from heavy steel cables between structural upper floors. Large computer-controlled hydraulic pistons anchor the giant suspended weight to the inner concrete structure, monitoring motion thousands of times per second. When a powerful gust of wind pushes the top of the tower toward the left, the heavy suspended weight naturally sways right. This dynamic counterweight action absorbs the building's sway energy, keeping upper floor motion almost unnoticeable to human residents inside living spaces. Without this 800-ton hanging pendulum counteracting movement, the top floors could sway up to 3 feet during severe coastal weather events. With all 3 structural elements operational, the pencil-thin skyscraper stands fully prepared to face the ultimate test of nature's power. A severe winter gale sweeps across the Atlantic Ocean, heading straight for the dense, tower-filled grid of Midtown Manhattan. At street level, pedestrians struggle against intense 80-mile-per-hour wind gusts, blowing umbrellas inside out and tearing down signs. At the top of 111 West 57th Street, wind speeds hit atmospheric levels equivalent to a Category 2 hurricane storm system. Sensors installed along the outer glass walls register immense wind pressures pushing hard against the skyscraper's paper-thin profile. Right now, deep below the street, heavy steel rock anchors hold firm, preventing the massive concrete foundation from lifting even a millimeter. High above, high-strength concrete side walls absorb millions of pounds of bending pressure, flexing slightly without developing structural fractures. Inside the upper mechanical room, the 800-ton suspended pendulum swings smoothly into action as designed by computer models. As a sudden wind gust shoves the tower east, the massive steel weight moves west, instantly dampening the building's natural mechanical resonance. Inside the upper luxury living rooms, glass water surfaces stay calm, while 80-mile-per-hour winds howl directly outside the glass. The complex integration of shape, mass, materials, and active damping performs perfectly, taming the fierce forces of the storm. As the Atlantic gale moves off into the ocean, the tower stands completely unyielding, completely undamaged by the intense dynamic loads.
The impossible engineering experiment has proven itself in real time, validating years of intense mechanical modeling and dangerous high-altitude work. The success of 111 West 57th Street has forever changed how structural architects and urban planners view hyperdense city skylines. It proves that humanity can construct exceptionally safe, stable, super tall structures on land footprints once considered far too small to build on. Around the world, growing megacities facing extreme land shortages are now studying this needle-thin tower as a blueprint for future growth. What once seemed like an unsafe architectural gamble is now recognized worldwide as a triumphant masterclass in high-tech structural mechanics. Every slender line of this building represents a triumph of human ingenuity over physical limits once thought completely impossible to break. It stands as a testament to thousands of ironworkers, engineers, and architects who dared to build into the sky despite intense skepticism. When we look up at this impossibly thin glass needle cutting through Manhattan clouds, we are seeing physics redefined before our eyes.
The lights of this city promise so much. It is up to us now to ensure that promise is realized by everyone who calls this great city home.
Proof that even on the tiny footprint of a city lot, human ambition can reach unprecedented heights and touch the sky.